Good morning. Today we're going to start chapter 10. We're going to circle back to chapter 2 and look at linear regression again. So we are starting section 10.1, simple linear regression, and we're going to look at all the inference behind it. Today is March 30th. Our learning objectives are to examine the statistical model for linear regression, and we're going to go through our simple linear regression model from the past. We're going to look at how to estimate our parameters. We're going to run confidence intervals and significance tests on linear regression, and we'll briefly look at the prediction intervals that are associated with the unknown. Remember, you can stop the video at any time if you need to catch up on your note-taking skills, and you're looking for those pretty sand-colored notes. So if you recall in chapter 2, we would be gathering data on two quantitative variables. And from those two variables, it's possible that we can create a scatter plot. And if there is any kind of linear pattern, it should reveal itself in the scatter plot. Remember, we have an explanatory variable and a response variable y. And we can use the least squares regression line, if it's present, to make a prediction for an unknown y value for any given value of x. So in chapter 2, we used this formula, y hat equals b sub 0 plus b sub 1 times x, to make a prediction for an unknown y value. And we know that this represents a straight line relationship. B sub 0 is our y-intercept, and b sub 1 is our slope. We can input any value of x that we like to predict what y might be. We could also work backward. If we have a predicted value for y, we could figure out the input value of x. Remember, when we gather our data, a larger sample from your target population is the best, and it will be the best way to draw some inference from. So these are the questions that we're trying to answer when we're looking at our simple linear regression. Number one, is there really a linear relationship between x and y? Or is it just happening by chance? And I guess that will depend on your sample and through repeated trials. Of course, when you do linear regression, we're looking at the slope or rate of change that relates x and y. Remember, there's always going to be a margin of error due to variation. If you do create a linear regression equation, how accurate will it be to make a prediction? Remember, once we go outside that graph, we're extrapolating, and it may not be reliable. So based on what we can see, can we get an accurate prediction when we come up with our least squares regression line? Or is our data too scattered for that to be an accurate predictor? Here's a scatter plot. What this represents is the eruptions of the Old Faithful geyser. They looked at how long the duration was of the eruption and then the interval in minutes between each eruption. And they're telling us that they have recorded 222 pieces of data. So what they did is they took their information and they created a least squares regression line. Based on their line, they're saying that the slope is 10.36 and the y-intercept is 33.97. When I look at this, the data seems fairly scattered, maybe more of a moderate than a strong. So is the least squares regression line going to give us an accurate prediction? Maybe, maybe not. But they're not showing anything beyond a 5-minute eruption. So if there is anything that is beyond that, we could be extrapolating and it could be inaccurate. So what if instead of looking at all 222 eruptions, we take simple random samples of 20 eruptions at a time from that population of 222, and each time we calculate the least squares regression line, and we'll stick with what we know for now. So you can see in sample 1, the blue dots represent the population of 20 that were randomly selected, and here's y hat. We've got an intercept of 32.8 and a slope of 10.2. So we're going to run this trial again. In the second sample, again, they've selected these blue dots. Y hat now has a different equation. We have an intercept of 44.0 and a slope of 7.7. So both of these are different than what we saw in sample 1. Same thing with sample 3. Again, the blue dots. We now have a slope of 9.5 and an intercept of 36. So what we can see here is that with our simple random sampling, we do have some variation present. So when we're writing our own regression lines, know that there's your margin of error. We have some kind of variation in our slope and our intercept based on just random sampling. Now what we want to do is move into an inference procedure. So we're still going to use the same format for least squares regression that we're used to, but now we need the true parameters. Well, we know that we don't typically have the true parameters, but we're going to make a shift in our regression line. So instead of predicting y hat, we're predicting the mean response for y. We're going to use beta. So beta sub 0 will still represent our intercept. Beta sub 1 will still represent our slope, and x is our input value. We're using beta to represent our true parameters, but we'll have to use unbiased estimators. So we're going to use this new statistical model for our simple linear regression. So for each value of x, we should have some value of y that can also be observed. Remember, we're under the impression that our response variable y is normally distributed because we believe that our values of x are also normally distributed. Instead of looking at individual samples, though, we're using x values as a mean. So we're looking at the mean x instead of an observed value of x. Remember, means will make your information more accurate. What we're looking at here is the model that develops our new regression model. What we want to realize is we're trying to predict the average response for y along this left-hand side. So what we want to do is look at the values of x's as separate subpopulations. So this first curve here, furthest to the left, this represents some value of x, maybe x is 20. But the output value for y can vary. What you're noticing here, this would be the mean value for the response value y when x takes on a value, like we said, 20. But then what if x takes on a value of 30? Maybe it's the center distribution. Well, when x is 30, the response value for the mean y also can vary. This center represents the average response. The same thing is true. Maybe in this last curve, x is 50. But when x is 50, the average response could vary. So in the center, we have our average. This regression line then connects all the averages for all the possible values of your random variable x. So we're getting a straight line function, but we're taking into account all the possibilities. We are trying to eliminate some variation, although some will always be present. So again, each distribution that we saw in the model, we want to consider a different subpopulation of x. So it's always a possibility that x takes on some random value. So what we're seeing in our regression line is how y will vary for each different subpopulation of x. And you'll notice it does pass through all these means, and again, making it more accurate. So even though we're using the same process, using slope and intercept, because it's connecting the means, we should have a more accurate predictor for our simple linear regression. All right, that sums it up for today. The assignment that goes with this particular lesson is 10.30. I did scan it in case you don't have your book at home. I've also sent you an email with this data. If it's easier for you to import the data, you can do so. And like always, if you have any questions as you're going through homework, please call me at home. You can text me, or you can send me an email. Until tomorrow, have a great day.